All right, welcome to The Explainer. Blockchain. Yeah, you've heard the word thrown around, probably with cryptocurrencies or digital art. But what if I told you that at its core, it's really about a totally new way to build trust in a world where, let's be honest, we're often told to trust no one. So today, we're going to cut through all that noise and build a blockchain from the ground up to see how it really works.
So it really all boils down to this one question. I mean, think about it, right? Almost everything we do online, our banking, our social media, it all depends on some central company, some middleman, to keep things straight. But how do you create a system for agreement on a global scale when you can't, and probably shouldn't, just blindly trust whoever you're dealing with? This is the exact problem blockchain was built to solve.
You know, for pretty much all of history, our answer has been centralized systems. We put our trust in a bank, or a government, or a big tech company to be the referee. That's what you see there on the left. But what if there was another way? Well, blockchain proposes the decentralized model you see on the right, where the entire network of participants, with no single boss, maintains the official record. So to really get how that works, we're going to build one together, from scratch.
Okay, so where do we even start? How do you build a record that everybody can share and, more importantly, trust? A record that can't just be secretly changed or wiped out? Well, it all starts with the most basic building block, a block. So just imagine a block is like a single, super secure page in a giant shared digital notebook. It holds a bunch of transactions, who sent what to whom and when, but the real secret sauce here is something called a cryptographic hash. It's basically a unique digital fingerprint for everything inside that block. If you change even one tiny little detail, a comma, a number, that whole fingerprint changes completely.
And this is where the chain part of blockchain comes in. It's brilliant, actually. Each new block doesn't just have its own fingerprint, it also carries the fingerprint of the block that came right before it. This creates this incredibly strong interlocked chain. So if you try to go back and mess with an old block, its fingerprint would change, which would break the link to the next block, and then that would break the link to the one after that. It creates this domino effect, and it makes any funny business stick out like a sore thumb.
Right, so we've got our secure chain. It's all linked together. But now for the big question. In a system with thousands of people all over the world, who gets to add the next block? I mean, you can't just let anyone do it, right? It would be total chaos. You need some kind of powerful engine to keep it fair and secure. And that's the next piece of our puzzle.
This whole thing is called proof of work, and it's basically a giant global competition. You've got computers all over the world, we call them miners, all racing to solve a really hard math puzzle. The first one to crack it gets the right to create the next block and broadcast it to everyone. And for all that hard work, for proving their work, the winner gets a reward, brand new cryptocurrency. This whole process is what makes it so difficult and expensive to add blocks, and that difficulty is what keeps the whole network safe.
Okay, but wait. With all these computers racing, what if two of them solve the puzzle at basically the same time? Which block wins? Well, the network has this one simple, super powerful rule. The longest chain wins. Always. Because the longest chain represents the most computing power, the most work that's been poured into it. It's the version of the truth that has the most consensus behind it.
So this system is, incredibly secure. But there's a catch. There's this built-in tension. You can try to make it faster, like creating blocks every 15 seconds instead of every 10 minutes. But as you're about to see, trying to make things faster can really mess with that security in some surprising ways. See, when you're trying to move really fast, it's way more likely that two miners will find a block at almost the same instant. This creates these little temporary splits in the chain, where for a moment the network disagrees on which one is the real one. The blocks on the losing side of that race, they're called stale blocks. They're perfectly valid blocks, but they end up as orphans. They're just wasted work. And that's a problem because the more of these little disagreements you have, the messier things get, and the easier it might be for a bad actor to try and cause some trouble.
And this table just lays it out perfectly. It really shows you that trade-off. Research looked at two major blockchains, and you can see Bitcoin, with its slow and steady 10-minute pace, has a really low rate of these stale blocks. But then you look at Ethereum, which was designed to be much faster. We're talking 10 to 20 seconds a block. Well, its stale block rate is more than 16 times higher. That's a direct result of trying to be fast. And all that confusion, it has a huge impact on security. The same research figured out what it would take for that faster chain, Ethereum, to be just as secure against fraud as Bitcoin. The result was pretty wild. To get the same level of security that Bitcoin gets after just 6 new blocks, what we call 6 confirmations, a transaction on Ethereum needs to be buried under at least 37 blocks.
So this is why you have to wait around when you do a crypto transaction.
It's not just about getting into one block. You're waiting for more and more blocks to get stacked on top of yours. Every new block that gets added makes it exponentially harder and more expensive for anyone to try and go back and undo your transaction. It's like pouring more concrete over it each time.
Okay, so we've built this secure shared ledger. It's great for tracking money, for tracking who owns what, but what if we could put more than just transactions in there? What if we could embed actual agreements, actual logic? This is where this incredibly powerful idea of smart contracts comes into play.
And what's crazy is that this idea from a computer scientist named Nick Szabo came out way back in 1996. That's more than 10 years before Bitcoin was even a thing. His whole idea was to take the rules of a contract and just build them directly into our digital world, so they could enforce themselves.
Szabo used the perfect analogy to explain it, a simple vending machine. He called it the primitive ancestor of smart contracts. Think about it. It's a contract built into a physical object that automatically enforces a simple deal. If you put the right amount of money in, then you get your soda. No cashier needed, no judge. The machine is the contract.
So a smart contract is just that. It takes that vending machine idea and puts the code onto the blockchain. It's just a program that lives on this decentralized network, which means it can't be stopped, it can't be changed, it just runs automatically, executing the terms of an agreement. If this happens, then do that, without anyone in the middle. And in Szabo's original thinking, these contracts are trying to achieve four main things. They should be observable, so everyone involved can see what's going on, verifiable, so you can prove what happened. They should have privity, meaning they're private just to the people who need to know, and the big one, enforceability. You want them to just work on their own, to be self-enforcing, just like that vending machine.
All right, so we've built this thing from the ground up. The blocks, the chain, the proof-of-work engine. After all that, what's the one big thing you should really walk away with about how these systems actually operate?
It really all boils down to this one major trade-off. The very mechanics of proof of work create a direct conflict between speed and security. If you want to make a blockchain faster by having blocks created more often, you will almost always get a higher rate of those stale blocks. And that, in turn, can weaken the security of the whole system, meaning you need a lot more confirmations to feel safe.
So the next time you hear about some new project that claims it's the fastest and the most secure, you'll know to be a little skeptical. Understanding this stuff, the chain, the proof of work, and especially this speed versus security trade-off, lets you see past the hype. And that's the key, right? It lets you ask the real questions. Are we looking at the foundation for a whole new internet, or are we just looking at a beautiful but really, really complicated machine?